Hello, I'm Steve Mann and this is Paper Classroom. Welcome to another one of our fibre tutorials. This particular tutorial is all to do with the page equation. The page equation is one of my favourite equations, formulated by Dr. Derek Page of PPRIC in Canada. And the page equation is virtually the basis of all paper physics. Now, this is the page equation. A little bit frightening, I would think. Looks a little bit frightening, but we can actually break it down into something very simple. We're interested in 1 over T, the tensile strength, Z, zero span strength, and B, the bonding contribution. What we're going to do is to just simplify this equation. 9 over 8 is a constant, G, gravity, is a constant, C is the coarseness of a fibre, 12 is a constant, P is the perimeter of the fibre, L is the length of the fibre, RBA is the relative bonded area between fibres. All those are just little tweaks. What I want to do is to just give you a simple version of this first of all, and then hopefully you'll understand it. Those are the 3 terms. This is essentially the page equation, and all the other bits and bobs just refine it. But if you understand this, you understand everything. So this is my stripped down version of the page equation. Now, what Derek Page did was eventually come up with this page equation, and you may have heard me use the word hornification. He was the guy that coined the word hornification, and he was a genius. There's no 2 ways about it. And it all started off when he was putting bits of paper in a tensile tester and measuring the tensile strength. Whereas most of us take the piece of paper out the jaws, throw them away, what he did was something very simple. He took the paper from out of the jaw of the tensile tester, looked at it under a microscope, and what he found was 2 things. He found that there were bits of broken fibre like this. So that means there was a fibre, and when the paper snapped, the fibre broke. And he also saw complete fibres that had not been broken. So what he inferred from that was there were 2 fibres that were crossed over at some point, and in the action of pulling the fibres to snapping point, rather than the fibres breaking, the fibres came apart. So the bond between the fibres broke. So that's what this is all about. When you snap a piece of paper, 2 things happen. Either the fibres break or the bond between the fibres break. And that's what this is all about. Now, he tried to look for a mathematical model to describe this, because this is what academics do. And he likened it to 2 resistors in an electrical circuit. Now, if you have 2 resistors in an electrical circuit, then the current passes through. It all depends on the values of the resistors to what the final resistance is and where the electricity goes. So if both resistors have exactly the same resistance, then electricity will flow equally between the 2, across the 2. If this is a big resistance and this is a small resistance, then a little bit of electricity will go that way and most of it will go this way. So the formula for calculating the resistance where you have 2 resistors in parallel is this: 1 over RT, the total resistance, equals 1 over R2 plus 1 over R1. So he saw the similarity between that and his model. So in here, sometimes electricity goes one way, sometimes it goes the other way. With the fibres, sometimes the fibres break, sometimes the bond between the fibres break. So it's a good start for a mathematical model. So what he did was he took that and he said, well, that's the equation we'll use, and we'll just swap the figure or the letters that the electricians use for appropriate symbols for paper makers. So the first thing he did was, we're not measuring resistance, we're measuring tensile strength. So he replaced R1 with T for tensile strength. Then we don't have a resistor here, we have the strength of the fibre. So we'll just put an F for now. And then again, we don't have another resistor, we have the bond strength or the bonding contribution, the strength taken to break that fibre-fibre bond. So we replace that with a little b. So this is now the simplified form of the Page equation. 1 over the tensile strength equals 1 over the strength of the fibre plus 1 over the bond strength. Now those of you that are quick and may have noticed that in the original equation I gave you, this wasn't an F, this was a Z, and I'll show you now why it was a Z. These equations are only really useful if you know 2 of the variables, then you can calculate the third one. Well, the tensile strength, we can put our strip of paper in the tensile tester and we can pull it apart and we can measure the tensile strength. But we cannot measure the strength of the fibres and we cannot measure the bonding contribution. So this is where the guy was a real genius. He said, well, if we can't measure one of those, we will measure one a different way. So we've got a choice. You can either measure the strength of the fibres or you can measure the strength of the bonding contribution. And Derek Page came up with a way of measuring the strength of the fibres. He invented a brand new piece of kit known as a zero span tensile tester. Now, with normal tensile testing, you have the top jaw and the bottom jaw and top jaw, and there's typically 180 millimeters difference. In his new piece of equipment, there was 0 difference. So we had the left jaw and the right jaw right up to each other, and the paper slipped in between. And the jaws pulled apart, and because there was 0 gap there, there's no opportunity for the fibres to slide over each other. Therefore, there's no opportunity for the bonds to break. The only thing you can break is the fibre. So now we have the long span tensile strength, we have the strength of the fibre, and the only other unknown is the bonding contribution. We can calculate the bonding contribution. So there's the equation again. So tensile we can now measure, fibre strength we can now measure, bonding contribution we can calculate, and because we measure this on this zero span tensile tester, he changed the letter to Z. So that's the original stripped down Page equation that I showed you at the beginning of this tutorial. And then he did a series of experiments. He took some virgin fibre, made a piece of paper out of it, so 0 recycles, measured its tensile strength, and from that same strip of paper measured the fibre strength and then calculated the bonding contribution. Then he mashed up that paper, turned it into another piece of paper, so one recycle, and again measured the tensile strength of the recycle fibre, of the recycle sheet, or the sheet made with recycled fibre, measured the strength of the fibre, calculated the bonding contribution, and then he recycled it again and again and again. And this is what he found for the tensile strength. He found that the more times you recycle it, the poorer the strength of the sheet. Well, we all know that's true. But the question is, why? Why does the strength go down? He measured the strength of the fibre, and look at that. Very little change in the strength of the fibre. So the fibre does not go significantly weaker. But the bonding contribution goes weaker. So when you're recycling fibres, what's important is the bond strength between the fibres, not the strength of the fibres themselves. So there's your tensile strength, goes down with number of recycles. There's your fibre strength, very little going down. And there's your bonding contribution. So this is where he came up with a theory that the bonds between the fibres must be reducing. Why are the number of bonds reducing? Because there is less contact area. Why is there less contact area? Because the fibres are stiffer. And this is where he came up with the term hornification, fibre stiffening. And here's a slide I've shown you on 2 or 3 other videos. With the virgin fibre, you have this very flexible fibre that will give you a lot of contact area, therefore a lot of hydrogen bonds, and therefore good bond strength. When you've recycled that fibre, you can't pump as much water in, it's stiffer, the contact area is reduced, therefore the number of hydrogen bonds is reduced, therefore you have a weaker piece of paper. And you recycle it again and it gets even stiffer, etc. So this is what the page equation is all about, and knowing that allows you to form a strategy for dealing with recycled fibre. And what you should all remember is everybody uses recycled fibre. Even virgin mills use recycled fibre because they put their broke back into the system. That broke has been dried once, so it's recycled fibre. So now we know why recycled fibres form weaker sheets, then we can work out what to do to reduce that effect. So if we recycle our fibres at higher pH, then the high pH will cause the fibres to swell, then we can get more water in, then they'll become more flexible, then you'll get more contact area and you'll get a stronger sheet. Well, I hope that makes sense to you. As I say, it's one of my favourite equations. Thank you very much for watching this video. I hope you enjoyed it as much as I enjoyed making it, and please give us some feedback and enjoy all our other videos.